involving integration and partial fractions. If you haven't seen that, go back and watch it, because it's going to got the introduction to the topic as well as example 22. So we're on to type 2 of our partial fractions types, which is what happens when there's a repeated linear factor. We already know from example 21 that if we're trying to deal with just a linear factor, we're going to end up with some kind of log expression. Okay. What we're going to come across here as well as that, we've got an extra thing to add into our toolbox, which is we're going to end up with integrals involving powers of that linear factor. Because it's a repeated factor, we're going to have squares or cube terms. And that takes us back to previous integration, where we can just recognize that as ax plus b to the power -2, a straightforward polynomial integration. So there's nothing too complex about those parts. So again, it's just about building up our solution. So example 23, find the indefinite integral 5x plus 2 over x plus 2 squared. There's your repeated factor, plus times x plus 1 with respect to x. So as we did before, we're just going to isolate the actual rational function, and we're going to consider how we might write that in partial fractions. First thing to do, check the orders. Do I need to do any algebraic long division? The order of the numerator is 1. The order of the denominator is going to end up as being 3. We've got an x squared term times x. That would give us x cubed in the end. So we're good to go with our algebraic, with our partial fractions template. So the normal rules are, we've got a repeated factor, so we've got some constant a over x minus 2 plus some constant b over x minus 2 squared. And we've also got some constant c divided by x plus 1. And that's all my fractions set up and ready to go. I can multiply through by the denominator here, which is x minus 2 squared times x plus 1. On the left hand side, that will completely cancel out with the denominator and leave me with 5x plus 2. And as we go through each of the fractions in turn, the x minus 2 will cancel with one of the x minus 2's in our red multiplier, and I'll be left with 1 x minus 2 multiplied by x plus 1. The b term will fully would cancel with the x minus 2's, which will leave me with x plus 1, and the c term will cancel with the x plus 1, so we'll be left with x minus 2 all squared. That's us got our equation that we can then start to think about evaluating a, b, and c. So try and find values of x which will simplify the expression. An obvious one would be to let x equal 2, and that's going to eliminate both the a and the c terms at the beginning. So we've got 5 times 2 plus 2 on the left. The a term is going to go to 0, and the b term will end up with 2 plus 1. The c term is going to go to 0 as well. So we've got 12 is equal to 3b, which means that b has a value of 4. What else could we evaluate? We could, if x was -1, then our a and b terms will disappear. So we end up with if x equals -1. On the left hand side, we've got 5 times -1 plus 2 is equal to, well, the x plus 1 will go to 0, so a term will go to 0, b term will go to 0, and we'll end up with c times -3 squared. So we've got on the left hand side, -5 plus 2 is -3, and then we've got -3 squared is 9, so we've got 9c, which means that c has a value -1/3. And we want to work out the value of a. So we've got a couple of ways of going about it. We could nominate another number, we could consider or equate any of the terms. One of the ways we could do it, just set x equals 0, That's another one. I'm going to do it actually on the right hand side. Don't run out of space. So if x is 0, what happens? We've got 2 on the left hand side. On the right hand side, we're going to be left with a times negative 2 times 1 plus b times 1, which is just b, and then we're going to plus c times negative 2 squared, which would be 4. So I've got 2 is equal to negative 2a plus b plus 4c, and substituting in the values of b and c that we already know, we can say b is 4, 4c is going to be 4/3, negative 4/3, my apologies, because c is negative 1/3. And if we rearrange all of that, we could say that 2a is equal to, if we subtract 2 from both sides, we get 2 minus 4/3, which is 1 1/3, which says that a is therefore 2/3, which means that a is going to be 1/3. You can work that out in your own time if you want. So it tells us our constant values of a, b, and c, which means that we can consider the original expression, which was 5x plus 2 over x minus 2 squared times x plus 1 is equal to, well, we had a over x minus 2, and a is 1/3, so we've got 1 and a 3 there. And then we had b over x minus 2 squared, and we know that b was 4, so we can put that in there. And then we had c was just your x plus 1, and c works out as negative 4/3, so we're going to end up with, well, c was negative 1/3, so we've just got negative 1/3. Okay, so there's our original rational function written as partial fractions. So what are we here to do? We're actually here to find the integral of that. So the integral of 5x plus 2 over x minus 2 squared times x plus 1 dx is now going to be the integral of all these three functions: 1/3 x minus 2 plus 4 over x minus 2 squared minus 1 over 3x plus 1 dx. Okay? Now I can do things to simplify the look of that. I'm going to split them up into three integrals. I'm going to bring the constant terms out. So I've got 1/3 of 1 over x minus 2 plus 4 times, and I'm going to make that a negative index there. And then I've got minus, oops, I haven't actually put the integral there, plus a, yeah, I'll just put that in there like that, and then minus 1/3 times. It's more important for the fractions here that the integrals are there, but you can do it whichever way you like. At this point, the linear functions are going to become log terms. Just watch in case you need to put, if the derivative of the inside function isn't 1, you're going to have to divide by that. So derivative of x minus 2 is 1, so no change there. The integral of 4 times x minus 2 to negative 2 becomes 4 times x minus 2 raised to the power by 1 divided by the new power. We'll sort that out. And then we've also got minus 1/3 times the natural log of x plus 1. Again, the denominator, derivative is 1, so no need to divide through by anything else. And we can just tidy that all up. That's 1/3 times the log of x minus 2 minus 4 over x minus 2 minus 1/3 times the log of x plus 1 plus c. And that would be our answer in this case. So we're doing, our integrals involve natural logs, but also we're going to involve, in this case, just a polynomial integration as well. And you'll find these happen when we've got our repeated linear factors. Okay, one more example, example 24. when it comes to irreducible quadratics, see what happens when we come across these. Okay.